Hello, thank you for your listening. I would like to show you about modular photodiode pinhole array solved X-ray imaging system on Sino United Spherical Tokamak in Tsinghua University. Sino United Spherical Tokamak, we call it SONIS, is a small spherical tokamak. Here is the main parameters of SONIS. We can see the torpedo field of the SONIS is less than 0.3 teslas, and plasma current approximately 50 kiloamperes and pulse length approximately 15 meter seconds. Here is an overview of soft X-ray imaging system I will introduce to you. The system consists of 7 arrays and 112 diode channels in total. All arrays are mounted in a model. The system has approximately 1 cm spatial resolution and 2 microsecond temporal resolution. Apart from the diode models built in Plasma, we have amplifiers and other electronics, and also well-shaded transmission lines as their interface. The system is powered by battery packs controlled by a switch model, and the switch model is triggered periodically. The diode arrays from optodiode crop is applied and soft X-ray detector, and the responsivity of the soft X-ray band is approximately constant, 0.25 ampere per watt, and the raise time is about 500 nanoseconds, so the detector is sensitive and quick enough to deposit soft X-ray radiation. The array has 16 elements and it outputs current in microampere range. All arrays are mounted in compact models. The model is made of low oxide materials and is small enough to install inside the vacuum chamber wall. Here is the structure of the model. The piece of array is fixed by the base made of aluminum ceramics. Flexible printing circuit is placed between pins of arrays and holes of ceramic, base with ceramic rules and screws to keep in electrical connection with pins. Twisting shield and adjustable pinholes control the soft X-ray intake without the interference of unexpected hard X-ray. The position for beryllium for filters is reserved. Compact stainless steel shields can be installed to required location on the inner side of vacuum wall by skeleton. Shieldings and transmission lines is one of the most important parts of the system. Instead of enameled wire shielded by stainless steel tubes, transport printed circuit shaded by multi-layer copper polygon bauxite is used, and here we call it FBC. FBC needs less space than enameled wire, and is more flexible and provides better shielding performance. Moreover, the multiple FBC interface provides stable electrical connection is designed, so the diode model can move everywhere. Here shows details of FBC and its interface. Figure A and Figure B shows the interface on feed-through to connect feed-through pins and pile of FBC using positive components. Stainless steel tubes and spring inside holes of positive component keeps electrical connection of pile of FBC. Figure C shows stainless steel component on the model to fix FPC and leading out signals. FPC is provided by a fixed copper wire here. Figure D shows FPC in the model. The pad in left side is connected with another FPC in the interface in Figure C, and those on the right side are connected with diode arrays by ceramic rules as we introduced. Two-stage transimpedance circuit is used as amplifier on the atmosphere side of the feed-through. The bandwidth of the amplifier is 700 kHz, and the first stage of the amplifier has a gain of 250 kW per ampere, and the second stage is designed as a voltage follower. Here, a specially designed filter between two stages is used to reduce electronic noise. Additionally, some principles in high-speed circuit design were used here. Because the current signal from the delta array is in microampere range, the strip-line circle is designed in printed circuit board to avoid disturbance. The theoretical electronic background noise of the whole system, including the array, the transmission lines, and the amplifier, is less than 1 millivolt. However, the sampling rate of data acquisition system we have is only 500 kHz, and it makes the temporal resolution of the system limited. This will be changed in the future. Battery packs is used as power supply of their arrays and amplifiers to avoid the electrical disturbance caused by DC power supply with AC inputs. A two-stage switch model with a series of relays controls the power supply. At the first stage, the switch model is triggered by the timer, then the relay of the first stage closes and triggers the relays of the second stage. Unlike the chosen battery packs supplies power. Because the discharge duration of SONIST is less than 100 milliseconds, the system is said to be triggered 1 second earlier than plasma discharge, and the length of the single operate duration of the system is 2 seconds, compared with 6 minutes short interval. So, the soft X-ray system works in a low power consumption and low duty cycle. So cooling turbs are inessential for the system, and we can make it much more compact. Here we can see where the models are installed in SONIST. Figure A shows the life of slide of the soft X-ray imaging system, as the models are installed on the low field side of the polyidal cross-section. The bulk plasma region is fully covered. Figure B is a photograph of the location of the system. The system is fixed by steel skeletons and cross horizontal magnetic probes in SONIST. Now, the result of the system is shown here. This is a temporal evolution of the voltage signal of the multiply array. The signal-to-noise ratio here is very high, and 10 volts ridge line integrated soft X-ray signal is obtained, compared to background noise which is less than 10 millivolts. In the experiment, the plasma is only ohmicated to get 25 kiloampere plasma current. A small-tooth oscillation of approximately 2.5 kHz is observed. Let us zoom in the time when oscillation occurs. Here we can see a reverse surface of small tooth exists between channels bearing plasma core and those bearing the edge. The former wrap up slowly and then collapse. The latter appears an upright when the collapse happens, and then they wrap down slowly. Here shows more parameters of the discharge. We can see the small tooth oscillation is not isolated. Periodically decreasing plasma current is accompanied by an uprush in low voltage and carbon-3 radiation, and also collapse from core regions of X-ray is at the same time. However, hydrogen alpha radiation shows no clear trend at the same time. Because plasma parameters on SONIST is low, so we can see that hydrogen alpha radiation comes from the H region, and the carbon-3 radiation comes from plasma core. So, here is evidence that the small tooth is related to energy transport from core to the edge, accompanied by a decrease in plasma current and temperature. To obtain emission profile for soft X-ray on SONIST, a tomography scheme for mobile modular soft X-ray diode arrays has been developed. The tomography scheme applies Tikhonov regularization method and Alcove criterion. What's new here is some algorithm tricks are used to get geometric matrix in real time with minimum calculation. So it is suitable for mobile modular arrays. Here is a test of tomography scheme with 5% random disturbance added into virtual line integrated signals. We can see that the solution reconstructed the main characteristics of the real image. Relative error in book plasma region is less than 10%. However, relative error in plasma edge and limiter region goes up. For plasma edge, it is because inversion precise is sensitive to the derivative of the emission profile. For limiter region, it is because more information of set construct and emission structure is needed. And here, we just show the test image, and the real experiment data reconstructed will be used for testing this month. Here, we can give a summary of the whole system. A new soft X-ray imaging system based on modular photodiode pinhole arrays has been built on SONIST, and the spatial resolution of the system is about 1 centimeter, and the temporal resolution is about 2 microseconds. Signal with high signal-to-noise rate is obtained due to well-designed electronics and shielding system, which is one of the most important improvements of the system. The other important improvement is that compact diode models, accompanied with demoldable and flexible transmission lines, is designed, and the diode models can be installed to any required location inner side of the chamber wall. Apart from the hardware, a tomography scheme for a movable modular soft X-ray imaging system has been developed to obtain local emission profile for soft X-ray on SONIST. Here is a reference of the work and acknowledgements. Thank you for your listening.